Yeah, very good evening to all. I'm audible to you. Yeah, is my voice is clear? I'm audible to you. Can anyone respond in chat box? May I know the response? Sorry for delay. I have some technical issue while joining the live. Very good evening to all. So good evening, Lata. Good evening, Saras. So good evening to all. I am audible to you. So my voice is clear. Can anyone respond in chat box? Yeah, okay. Yeah, good evening, Pavitra. Good evening. Thank you for joining. Thank you for your presence. Today's day 12. Today we are gonna see RAM. So we are gonna see how to write a Verilog code for single port RAM, and we're gonna see also what is RAM. So what is the purpose of RAM? Why we are using? So how we can write the Verilog code for that? So single port RAM is a basic RAM model. So by using, if you understand the single port RAM, you can easily understand how computers, how electronic devices using RAM, how it is works. So we'll see in this session, and also we'll try to write code for ripple carry order. So this is also an important question: ripple carry order, ripples carry skip order. So these are the important questions also. So thank you for joining. So very good evening to all. So let's wait for few minutes. So there are 49 members only. Let's wait for few minutes. Remaining people have to join. So good evening, Steve Krishna. Twin Sync, good evening. Chaitanya, good evening. Yeah, Mikey, good evening. So very good evening to all. So we're gonna see only RAM, single port RAM, and then triple carry adder. So we're gonna write the RTL code, Verilog code for that. So so I think let's start the session. So thank you for joining. So we'll go to the RAM. So RAM is a random access memory. So this is a volatile nature. So volatile nature means it will store the data temporarily. While if you switch off your computer, it will erase the data. While on the when you switch off the computer, it will erase the data. So this is a RAM. So RAM is mainly used for it is a computer storage for temporary memory. So how can we using means, so our if you buying a mobile phone or a computer, we will see a 6 GB RAM, 8 GB RAM memory. So it all the temporary memory only. So our main OS is stored in SSD or HD hard disk. So our main OS is stored in SSD, and then if you while you starting or while you switch on a computer, you can notice that like BIOS setup, well, like it will start like you can see in the black screen while you're booting, but basic input output system. So so for that, firstly it BIOS must be start. They for that they need, so some if you start your computer, you need a BIOS will be must be start. For that BIOS, we have to give some instruction for that. To start our computer, firstly we have to boot, and then we have to boot our OS. For that we have to start the BIOS. So for that it need instructions. So that instructions are stored in ROM, so read only memory. So it is a permanent memory. That particular instructions only are stored in ROM, and then it will get from the ROM. It will BIOS get the instruction from the ROM, and then BIOS will start booting the our OS. So after booting the OS, that some important instructions or memories we need to run the computer processor. For that they are using the RAM memory. While running, if you turning on and putting on your computer, it will use the RAM memory to run the computer smoothly. So how many tasks you are doing, based on that your speed will be declared. So if you are using multitask, your speed will be low. So if you are using multiple tabs in your computer, your speed also may be low. Same like that. So we have the OS in the SSD, we have the instructions from the ROM, read only memory. So the BIOS, the booter, so it is a booting system. It will boot the instruction from the ROM, and then it will start the OS booting. If you are using Windows, it will start the Windows OS booting. So for that it will use the RAM memory. So it is a temporary memory, it is a volatile in nature. While switch off your computer, it will erase the data. This is a main important thing of RAM memory. So there are a lot of varieties of RAM, like SRAM, DDR memory. So this all comes under the RAM category only. So this is the thing about RAM. So we are gonna in this see. So you can also see here, RAM is essential for starting the Windows. Without RAM, a system can't start, just like a car without fuel. So if you want to start the RAM, if you want to work on boot on OS, means Windows or any OS, you must need a RAM. Then only you can boot your system, operating system. So main thing is OS is stored in storage like SSD or SSD hard disk storage, and then BOS need a instruction. That important instructions are stored in ROM. It's on chip, it is a read only memory. It is a non-volatile in nature, so it will store the instruction permanently. And then every time if you are switch on your computer, it will give instruction to the BIOS. It is a booting system in your computer, so it will boot our Windows. So for booting Windows, the booting system are happening in the RAM memory only. So this is the main thing. So we're gonna see write the RTL code for single port RAM. So this is a basic architecture or basics of RAM. So we're gonna see in this session, and also we're gonna try to write the ripple carry order in Verilog. So very good evening to all. Thank you for joining. So let's get into session. So this is a single port RAM. So this is easy only. So there is a single port RAM and a dual port RAM. The difference between the single port RAM and dual port RAM is, if you are using single port RAM, you can write or read at a one. If you can't do both at a time. So if you writing into memory, you can write only. If you want to read, means you can read from memory. You can't do both things, like writing and reading from the memory. So this is the main difference. But in your dual port RAM, you can do simultaneously. You can write and read simultaneously. You can write for different address. You can read from different address. So this is the difference. So in the single port RAM, you have only address. You can do only read or write at a time. You can't do both time. You can't do both at a time. So this is the main thing. So this read and write operation based on the clock. So clock. So clock is every main thing here. So every passage of clock, it will go to some particular address. It will read. Sorry, if you are writing into memory, means based on your address, at the every passage of clock, it will go to the particular address. It will write the data, whatever given to data. It will write the data on the RAM. And then if you given a read, if you do read, means it will go to that particular address. It will read the whatever you given the data, it will read. So we can get this output. So this is the main functionalities of the RAM. For that RAM creation, you just need a clock, and then clock address. So clock address, and then write enable or read enable. So I am using here en is anything but enable. If enable is high, means I can write into memory. If enable is 0, means I can read from the memory. So read out from the memory. and then output is D out. So this is the signals in the single port RAM, the simple thing only. So based on these systems, so based on these signals only we can build the RAM. So if you taking dual port RAM means it have two address, read address, write address. So there is additional signals are added for the dual port RAM. If you take in like a FIFO memory or any other DDR, DDR3, DDR5, so these are the memory also we are being latest in the latest in your computer. So basically our, if you take in your computer current nowadays we have the some laptops and mostly laptops based on the DDR memory only, so DDR RAM. So DDR is a one kind of RAM, so it will transmit and receive, or it will do fastly computing and sending data. So we are using that currently, DDR memory, DDR5, DDR3. So these all things, DDR, DDR5, DDR3 comes under the RAM only. So you just first of all you just need to start from the single port RAM. Then if you done means you can easily understand what are the remaining things in the RAM family. So we'll go to the write the RTL code for the RAM. So this is my so I can, so basically my input signals are clock and write enable, write or read enable, and then D in, data in, and then let's check the address. So address also need, and then my output signals are only D out. So D out means data out. So we are gonna write the condition for that. So basically module single port RAM. So I'm just so I'm just write my port list here. So my port list input output signals are input. So clock is my first input, and then write or read enable, and then so these my two signals. So and then input address is my second signal, so sorry, third signal address. So I'm gonna write for 8*64-bit RAM. It means it having the 864 memory location. So in the RAM it having 864 memory location. In each memory location we can store the data up to 8 bits. So we can store the 8 bit of data, and then we having the 864 memory locations. So for the 64 memory location we need to give address. So for the address we have to follow the 2 power, so 2 power 2 power 6 equal to 64. So we have to give address for 2 power 6. So this is our address bit range. So we need 6 bit of address only. We need 6 bit of address to achieve the 64 memory locations. So for that I just write 5 down to 0 of address. This is my address. So I given like a address, clock, write enable, read enable. So and then we'll move to the output. Output is my output will be 8 bit of, so each and every location it store the 8 bit of data. So I just write it 8 bit of D out. Okay, this is my output. So and then I just missed here input. So my input also sound down to 0, it means 8 bit of D in. So this is my input output signal for the SRAM, sorry, single port RAM. So I'm gonna write now some registers. So reg sound down to 0, RAM 63 down to 0. It means it having the 64 memory location and 8 bit of each memory location. We can store the 8 bit of data. So this is a RAM creation. So and then adjust register my another variable like a 5 down to 0 address register. So and then in the always block, in the always block at the every passage of clock it will trigger, and then it will do execute always block at every passage of clock. Telugu. So if and then so firstly, so if the write enable, so write enable means if a write one means write, it will do writing operation. 0 means if the write enable signal it is it having 1 means it will do the writing into memory like a single port RAM. If it is 0 means it will do the reading out from the memory. So if write enable is high means it will do the read, it will do the write into memory. So for that RAM of address D in. So I'm just assigning my whatever it having that input data, I'm assigning to the memory, RAM memory. So imagine this is a memory, and then address. So here I'm giving some here also I'm giving some input here by using port list. I am giving some input for address. So if I give like a 0 means in the RAM 0th location I am assigning the value. So this is a difference. So this is I'm doing like in the particular address of the RAM I'm just storing the input value, and then else address reg I'm assigning the address. So I'm just assigning the input value from the address to address. It will do the write operation. If it is write enable is equal to, if it is 0 means, if it is false means it will execute this. I am assigning the address into our address variable. So you can see here this is my address register. Both are having same vector like a bit range 6 bit. Why I am using the other register means if I am using the same address for the read and write operation, there is a collision, there is a conflict between the signals. So there is a chance to get the unknown values or unaccepted outputs. For that I am using the additional register to read from the memory. So assign D out say RAM of address register. So I given only one address only for writing and the reading. So if my right enable is I, so I given some address 1, it will it will read the location. So in the first location, whatever it having, we will get the output. How means, if it is I means writing, if it is 0 means I'm assigning the same address. So I'm assigning the same address, whatever I'm written address, I'm assigning it here same address to assigning to the address register. So that address register, that I'm reading the same address register. So basically we using same address, but this address register I'm using for read. So this address is using for a write into memory. Both are having same, but for the conflict, to reduce the conflict between signals, to reduce the unknown set of my output, I'm using the additional register for read and write. So this is a circuit, this is a Verilog code for that single port RAM. I just save and run to check my output, to check my errors. So it is easy only. So if you are moving to single dual port or a DDR or a SRAM kind of things, you will get an confusion. It having lot of signals. So just we are moved to write the test bench here. Module test bench and module. So my signals are reg, clock, write enable, and then D, and then that's all for single bit inputs. Why I'm writing the clock and the write enable for continuously means both signals having the single bit wide only, but D in input signal having the 8 bit of wide. So for that I am writing separately D in, and then reg address, it having the 6 location, 6 bit address. So and then wire output 7 down to 0 D out. So and then you can also notice here I didn't write any reg here, reg keyword. Address register stores what kind of 6-bit data. So it will start from 0. So address will start from 6-bit means 0 0 0 0 0 0. This is a first location. So this is a second location 0 0 0 1, like that. Right after it will base it store the 6-bit of address. 0 0 0 1 2, like that. It will go up to 1 1 1 1 1 1. It's totally 6 ones. So it means 2 power 6. So it will go up to 64. So we have the memory location, 64 memory location. For identifying the memory location, we have to give address. So if you want to read the address means, if you want to read the memory means, you must need address, then only you can read. So for that I am using the address to identify the particular location. So why I am using 64 means 5 down to 0 means, so it will works like this only. So first location it having, you can imagine here it will start from 0 to 64 location. So my first location address is this, second location address is this, third location is this, like that up to 64. So why 6 bit means to achieve the 64 bit memory location. If I'm having the 32 means 32 memory location means I just need the 5 bit of data only. If you I just want to access all the locations, 64 location. For that I need a separate address. For that we have to use the 6 bit data only. So 2 power 6 means 64. No, 6 not a 6 address lines. It's like a 6 bit of address only. So and then we'll move to I just get a signal and then I'm do like a instantiation. So my model name is SP RAM, single port RAM A1. So and then I just to reduce my time I just follow this and then initial begin and then clock equal to 0 and then clock equal to 0 forever. So this is one state keyword like a forever at every 5 nanoseconds. It's like a always block. So while using the always block we are creating the clock same like that only. But we can't use the forever inside the always block. Clock will be toggling. So this is my clock creation. So and then initial begin. I just write a dollar monitor so in the dollar monitor I want to see output of my data in address. Firstly I want to see write or read enable. So I want to see in my binary and then we'll move to the write enable and then data in decimal and then data in data out in decimal. So and then we'll write the write enable and then d in and then d out. So firstly I just give some delay here and then firstly my write enable I'm going to write into memory. So write enable is high, it means I'm going to write. So my address is 0th location. My d in is 10. So I'm just save and I'm going to write a dollar finish at 20th nanosecond. I just finish my simulation. So after that I give some delay. Again I given like my right enable equal to 0. Now I'm reading data from memory RAM. My address is 0th only. So 1 means writing into memory. So 0 means right enable equal to 0 means I will read from the memory. Yeah, you can see here. So dot equal to dot equal to 10. So in the first in the which location, in the 0th location. Now I change here 64 location. I will read here from 64 location. So I'm writing into 64 location and then I'm reading out from the 64 location. So I'm getting the same things. So for the address denoting, we need some address. So for the writing into memory or writing from the reading out memory, we need the address. So totally we have the 64 memory locations. For denoting the 64 memory location, we have to write the 6 bit of address only. There is no lines like 6 lines of address, not like that. It's a 6 bit of address, that only. So I think we were totally clear. I think so. So for 64 location, we need the 6 bit of address for writing into memory, read from the memory. So I just I'm just in here. I'm going to write continuously. There is some delay here. I'm going to write for 50th location. My data will be the 16, and then copy this. So after that, my address location will be 23. My data will be 78, and then my address location will be 34. My address, my D and that location is 89. So or 78 kind of thing. So here I'm going to change my address. So I'm going to change address is firstly I'm going to read from 45 memory address location. After some delay, I'm read the 23 memory location, 23rd memory location. After some delay, I will read the 15th memory location, 50th memory location. So just save and run. So you can see here 78 from the 78 right enable 0 in the 78 D in 78, and then DACT out to 78. In the 78 D out to be 16. So this is a way of writing the RTL code of a 64-bit 64-bit single port RAM. So and then we'll move to the ripple carry adder. So we see in the 64-bit single port RAM how to write the Verilog code. We'll see ripple carry adder. Before going to that, this is a time for, if you guys are really interested in this master class, you can convert into the 1 month internship on FPGA design. So you will get the benefits of all 30 days organization, all 30 days presentation, exclusive project codes, VIP community group for our doubt clearing, and internship updates. And then you will get the IET certificate. It is a internship confirmation letter, and then you will get the 90 days LMS course access, and you will get the assignment and task, and you will get the weekly live sessions, and you will get the resume building, and then it is helpful for your while making your resume, and then mock test, internship certificates, and then you will get the participation certificate. These are the benefits you get from the 1 month of internship. We will give the internship at the free discounted fee of just 999. So regular fee is 399. So in this masterclass session time period, we are giving the discounted fee of at just 999. If you guys are really interested, you can use this internship program. So if you want means, you can use this registration link, and also you will get at the chat box. Our organization will post the link on chat box. So by using that, you can join our internship program. So this offer will close at 28 March. So this is limited time period offer, so you can avail it. So we'll move to the ripple carry order. So this is a ripple carry order block diagram. Yeah, one is right. If the in the RAM write enable is high, means I just assuming I am writing into memory. If it is 0 means I am reading out from the memory. So this is the logic of the single port RAM. Yeah. So and then we'll move to the writing of the ripple carry adder. So the name itself having the ripple carry adder. So it has consist of continuous full adder. So it will rippling the carry out. So you can see here, for each full adder we have to give like 3 inputs, A, B, C in, carry in, and then outputs are sum and carry, sum out, carry out. Here you can see that carry out will be input for next full adder. So there is the rippling of the carry. So that's why we are calling it a ripple carry adder. It use the previous full adder carry as the input. So if you take this input, if you take this full adder, this full adder needs this full adder carry out. So it just wait for compute all 3 things, like first full adder have to complete the execution. So on that time, the fourth full adder have to wait for the first and second and third full adder have to complete. Then only it will receive the carry for input. So there is a delay also while the ripple carry adder, but we are gonna write this code in the session. So this is a basic diagram for the ripple carry adder. Each and every full adder needs the previous carry out to compute the 4-bit adder, like a 4-bit ripple carry adder. So we'll go to write the RTL code for the ripple carry adder. So my inputs are 4-bit of A, 4-bit of B, and then C in, 4-bit of sum out, and then 1 C out. So these are my port list, and then you can see here wire C0, C1, C2. So this is act as a wire to transmit the signal from one full adder to another full adder. So mainly wire are used to connect the 2 blocks or 2 things. Same thing. So same thing here also, we are using wire here, C0, C1, C2. These 3 things are act as wire to connect the each and every full adder to give the carry input for the next full adder. So and then we'll move to the area playground. I'm just delete this. So for that, firstly I have to create one full adder logic, full adder. So my input signals are A, B, C in. My output signals are sum and C out, carry out. Assign sum equal to A XOR B XOR C in assign carry C out equal to uh, A and B or A and B or B and C in, and then C and D, C in and A. So this may carry equation. So I'm just going to create another design code, like if this is my ripple code, top level code, ripple carry adder. So my inputs and signals of the ripple carry adder. So I'm gonna just use this module to compute my ripple carry adder functionality. How means I'm just instantiating this module 4 times. So we can call this 4 times. So we can do the 4-bit full adder. So 4-bit ripple carry adder by instantiating this module 4 times. So I'll just show you how to instantiate 4 times. Means input 3 down to 0 of is this is a 4-bit of full adder. So 4-bit full adder, and then B, and then my input, another input is C in, and then my outputs are C out, some 3 down to 0, sum, and then another output is C out. So and then I'm just doing the instantiation of the full adder 4 times, and then I just create wire. So wire is one data type. We know that C1 is a one wire, C2 is another wire, C3 is another wire. Y means so I'm just, we can see here this full adder C out will be assigning for carry in the next full adder. This full adder C out will be assigning for C in for next full adder, same like this. So we need wire to assigning these operations. So 3 wire like as C1, C2, C3 I'm gonna use. So these are my wires. So I'm just instantiating my first full adder. I'm just calling this module again. So I can instantiate the first full adder, like this full adder module in my second ripple carry adder. So this is my instance name. So basically we know that instantiation A, I'm going to connect each and every signal A of 0. So I means this inside the bracket it will refers to the current module. So current module input is, we have the 4-bit of input, like a 4-bit of A. So it means it having 0, A of 0, A of 1, A of 2, A of 3. So 4-bit. But so our main logic, our main assignment here only, I'm gonna not write for this RCA here, ripple carry adder. I'm just calling this module and just I'm passing the input for this module in the current module. I'm just passing the input output signals from here to this module. So it will receive the signal, what values it will perform the sum and the carry out logic, and it will give the output. Same like I'm just instantiating and then I'm calling the module. It's like a structural kind of Verilog writing, Verilog code writing. So and then B of 0, and then C in, so and then sum, of 0. I'm just connecting the each and every signals. So this is my first 0th signal to the module, like each and every in the RCA module I have the 4-bit of signals. So I'm just connecting the first bit of signal to this module. So and then someone carry C out. So it will, this is a this C out is refers to destination module, like this module. So my output of the first full adder, so you can see here my output of first full adder is C0. It means wire. So I'm gonna use this wire to transmit the data to this full adder. So to send the data from this full adder to this full adder, I'm using the wire. So my wire is C1 is my first wire. C1 is my first wire, so just write here C1. So this is my first full adder. I just copy this. This is for second, this is for third full adder. So here my inputs are 1, third bit, 3 bit of AB is AB. Here also 1. C ins over here. So I'm just for the second full adder. For second full adder, for this full adder, it will receive the C in from the previous full adder. So previously I'm assigning the C1. So that C1 wire it having the first full adder output of C out. So I'm just assigning the C in for, and I just assigning for C in for second full adder. So it will come here, and then I will get the sum 0, sum 1 output. So here C2. Same here in here C2. Sum 2. Here C3. So here C3. Here sum 3. Here C out. This is my final C out. This is my final C out. So this C1 is my first full adder C out. This C2 is my second full adder C out. This C3 is my third full adder C out. I am assigning each and every output for the next full adder. You can see here next full adder input. So this act as input. This is a module for this scene is refers to this module. So this C2 is refers to current module. So and then this is the instantiating 4 times of full adder, we can achieve the ripple carry adder. So this is the thing. So I'm just gonna run this to check my errors. So A1 here I'm gonna change A2, A3, 2 different instance name. We can't give the same instance name for all instantiation. A2. Sorry. A2, A3, A4. Yeah, I didn't get an error, so just run the test bench. So I'm gonna write test bench for this module only. This is my top level module RCA. My inputs are read 3 down to 0 of the A and B, and then wire, sorry, C in. This is my input. So and then wire 4 bit of sum. So and then wire C out. These are my signals. just instantiating RCA replicate added A7 or A. So and then initial begin. So in initial begin here I'm gonna write firstly alt monitor. I want to see output like A, B, C, all the things. Okay. A equal to in binary, B equal to in binary, and then C in binary. So and then someone carry in binary, C out. So A, B, C in, and then someone carry, C out. So after some delay, I am passing inputs like A equal to 1 0, like a 4 bit of binary 1 0 1, and then B equal to 4 bit of binary 0 0 0 1 1, C in equal to 1 bit of binary 0. So after some I give some delay 10 nanosecond. Let's check the output. Someone carry. A is already declared in scope. Sorry, here A8. You can see here 1 plus 1 1 here 1 1. So if you add this like a 1 plus 0 1, and then 1 plus 1 0 1, here I am getting 1, so and then 1 here, so I am getting the sum correctly, CO correctly. I just add here another 1 to check my CO. So I'm just add another 1 here, so whether my CO is correct, it will give correctly or not. So I will get my CO equal to 1. Let's check. So you can see here my CO equal to also 1. So and then I will give some C in also 1. Let's see what happened. So otherwise I'll change one here. AB is equal to decimal. Sum in decimal. So and then you can see here 10 11 plus 20 21. I'm getting 21, but why here is 6 means first 4 bit, like if I change sum equal to 5 bit means it will I will get not I'm not get the C out. So this 6 means what means if 21 we can't like a 4 ones, like a 4 bit we can do up to the 16 only, so 0 to 15 only. So if you add some another one here means you will get the 21. So for 21 you need to declare in the 5 bits, then only you can do 21. That's why it will showing 6 here. So this is for writing the full adder code. So this is a main thing. So this is a structural model writing. So I am declaring one module. In the module I am writing the full adder logic for one full adder. I am just use this module again the 4 times. By using this I can achieve the 4 full adder, but my signal names are on the wires. I am using wires here to connect each and every full adder. To connect each and every full adder I am using wire. So this is a way of writing the structural model Verilog coding. So each and every time I'm calling this full adder, this module, and then I'm passing my inputs, and then I'm passing my inputs, and then I'm passing my inputs. It will perform assign statements, assign operation, continuous assignments, and then I will get my same output at the signal. So this is the way of writing the full adder code. So this is for today. So tomorrow we'll see the upcoming session. We'll see the new topics. Tomorrow we'll gonna see I think clock domain crashing. I think so. We'll do this clock domain crashing, and then we'll move to the FEJ implementation. So in the upcoming class we are gonna see like LED, basic LED blinking, and then how to create the clock in FEJ. So I means our FEJ or any FEJ it have in the clock oscillator, it may be 50 to 100 megahertz. So we need some delay here. So in the simulation we are giving delay directly by using these statements. But in the FEJ writing, if you want to add delay in your design code, you can't add any delay code in the module. In the design code you can't add any delay, and then you can't write the initial begin statement in the RTL code. In the design code you just need you can use only procedural assignments, like a procedural block, like always block, and then you can use assign statement, continuous assignment for the design code. And then if you want to add delay means you just need a counter. So counter is the basic things to add the delay. And also if you want to increase your if you want to decrease the frequency, the after the clock, your input clock is 50 megahertz, you have to decrease to 25 megahertz means you have to use the counter here. It's counter operation. So we'll see the upcoming sessions. I think we'll see the tomorrow counter. So it is important things. So by using the counter only we are increase and decrease the frequency by using the RTL code. So and then there is a PLL block in the Xilinx or Intel Cortex primes to create the code from hardware, from software, the Intel Cortex from software. And also we can write the RTL code for the logic for counter. So we'll see upcoming class what is counter and how to use the FPGA port. So thank you guys, thank you for listening. Yeah, using T flip-flop, correct. So thank you for your wonderful response. So we'll see tomorrow. Thank you guys.